Assalamualaikum warahmatullahi wabarakatuh, and very good day to all of you. So for chapter number 5, part number 1. In chapter number 5, we will discuss about the axial flow compressors. Okay, in terms of content, we will have I call the discussion about the velocity diagram for the compressor, thermodynamic equation, stage losses and also efficiency, stage reaction, stage performance, and the last one about the surging and also stalling phenomena for the compressor. Let's start with an introduction for the axial flow compressor. Okay, an introduction to the axial compressor stage. So the figure shows the cross section of a gas turbine engine. So now our focus is the I call the different stages of the compressor. So normally we will have in terms of main component of the gas turbine engine, we have for this figure we have low pressure compressor, LP compressor, high pressure compressor, high pressure turbine, and also low pressure turbine. So for this slide we want to concentrate on the low pressure compressor and also high pressure compressor. So if we redraw I call the component of the compressor inside the red box in the slide. So we will have the second figures, where the second figure shows the cross-section drawing of the compressor, including low pressure compressor and also high pressure compressor. And we call this system of the compressor as three-shaft compressor system. Okay, in the figures, the yellow arrow shows the direction of airflow into the compressor. In terms of main component of the compressor, so we have fan rotor that used to suck huge amount of air into the compressor. We have inlet guide vane. We have rotor represented by a green color blade. We have stator represented by blue color blade. And we have outer casing of the compressor, rotor drum, and also shaft. So why we call three shaft compressor system? So we call this compressor as three shaft compressor system because I call the location of the rotor of the compressor is located on different I call it on three different shafts. So we have the shaft that used to assemble the fan rotor. Second shaft used to assemble the rotor for the low pressure compressor, and the third shaft used to assemble the rotor for the high pressure compressor. So that's why this type of compressor we call three shaft compressor system. Okay, so if we zoom in the initial stage of the compressor for the low pressure compressor, so we will have this simplified circular diagram that consists of inlet guide vane, rotor, and also stator. Okay, and for the rotor we will have what I call an arrow that shows the rotational direction of the rotor. Okay, the combination of rotor and also stator for the compressor we will call, for this case we will call first stage of the low pressure compressor. So one stage of the compressor will consist of one rotor and also one stator. Okay, so this figure shows the actual features of the rotor that consist of rotating rotor blade, and the second one shows the actual features of the stator for the compressor that consists of static I call stator blade. Okay, for the inlet guide vane as shown in the figures, inlet guide vane actually is a stator, but we refer as inlet guide vane because this stator located at the located in front of a first stage of the low pressure compressor. And the function of the this inlet guide vane is to directing the flow away from the axial direction in order to provide the best angle for the first stage of the compressor. And this guide vane actually will accelerate the flow rather than decelerate or diffuse the flow. And its function is similar as turbine nozzle, where it increases the kinetic energy of the flow. So if you look at the schematic diagram of the guide vane, rotor and stator arrangement in terms of velocity profile, you can see throughout the guide vane, the velocity of the air will slightly increase. When the air flow through the rotor, the what I call the velocity of the fluid will drastically increase. After enter the stator, the velocity of the fluid will reduce because the energy of the fluid already decrease. Okay, but if you look at the in term of at the what I call the pressure profile in the guide vane, the pressure will slightly decrease. In the rotor, the pressure increase, and in the stator, the pressure value will be increased more compared to the pressure increase in the rotor, because the function of the compressor is to increase the air pressure. Okay, now we will discuss about the velocity diagram for the axial flow compressor. In terms of concept, the concept of the velocity diagram is similar as the concept of velocity diagram for the axial flow turbine as we discussed in previous chapter, in chapter number 4. For a velocity diagram of the axial compressor stage, so before we discuss the detail about the velocity diagram, so we need to look at the arrangement of the schematic diagram for the blade rows. So first we have the blade rows for the previous set of blade rows. If you consider numbers of stages in the compressor, or if we consider single stage compressor or the first stage of the compressor stage, we can consider this blade row as the inlet guide vane rows. And we have the airflow direction that represented by yellow color arrow. And the second arrows represent the rotor blade rows. So for the rotor blade rows, we have an arrow that shows what I call the blade rotation direction. And the third rows is for the stator blade rows. And condition number 1 or state number 1 represent the outlet condition for the previous stator blade or for the inlet guide vane rows, and also represent the condition at the inlet of the rotor blade rows. And condition number 2 or state number 2 represent the outlet condition of the rotor or inlet condition of the stator. And condition number 3 is condition for the stator blade rows condition. Okay, the combination of rotor rows and also stator blade rows is considered as a compressor stage, which is a compressor stage will consist of one rotor blade rows and one stator blade rows. Okay, in terms of velocity diagram for the outlet of the previous stator blade row or inlet guide vane rows, or the velocity diagram for the inlet for the rotor blade rows, so we need to implement the vector principle where we have relative velocity W1 plus blade speed U. So we will get resultant vector C1 absolute velocity. And the component of axial velocity for both W1 and also C1 is Cx1, which is also equal to Wx1, and X stands for the axial direction. So Wy1 is the y component for the W1 relative velocity, and y represent the tangential direction. And for C1 vector, so we have y component for C1 vector, which is equal to Cy1. And the absolute flow angle for C1 represented by alpha 1, relative flow angle for W1 represented by beta 1. Okay, so the velocity at the outlet of the rotor or at the inlet of the stator, so we have W2 relative velocity plus blade speed U, so we'll get the absolute velocity C2, and the axial velocity for both W2 and also C2, so we will have Cx2, which is also equal to Wx2. And Cy2 represent the y component for C2. Wy2 is the y component for W2. And the relative flow angle for W2 represented by beta 2. And the absolute flow angle for C2 represented by alpha 2. At the outlet of the stator blade rows, so if we consider a single stage of the compressor, so we will have only one vector, which is vector C3. So we have the axial component Cx3 and also Cy3, and the angle of the absolute flow for C3 is alpha 3. Okay, so these are I call the velocity diagram at important condition of the axial compressor stage. So we need to consider the inlet velocity diagram of the rotor. Velocity diagram at the inlet of the rotor, at the outlet of the rotor, and also at the outlet of the stator. Okay, in order to simplify the analysis of the velocity diagram, so we can consider a normal stage condition where we assume that absolute velocities and flow directions at stage outlet are the same as at the stage inlet, where we have, in terms of magnitude and also direction, absolute velocity C3 at the outlet of the stator is equal to the absolute velocity at the inlet of the rotor C1. Similarly to the value of absolute flow angle, where alpha 3 at the outlet of the stator is equal to the value of alpha 1 at the inlet of the rotor of the compressor. Okay, so in terms of compressor stage velocity diagram, so we have the velocity diagram at the inlet of the rotor and also the velocity diagram at the outlet of the rotor. So both velocity diagram will have same distance in terms of same value and also direction of blade speed. So we can combine both velocity diagram into one velocity diagram as shown in the slide. So if you compare the velocity diagram of the compressor with the axial flow turbine, so in terms of value, both the relative velocity W in the rotor and also the absolute velocity C in the stator are diffused in the compressor stage. Okay, are diffused. Where in the rotor, if you compare to the value for the axial flow turbine, so in the rotor, W2 is lower than W1 in the compressor, and in the stator, C3 less than C2 in the compressor. So in order, for example, when we analyze the velocity diagram, in order to determine unknown components, so we need to refer to the trigonometry and also triangle law. So trigonometry and triangle law need to be used to determine the unknown components of velocity vector. Okay, next we will discuss about the thermodynamic relationship in terms of enthalpy difference for the axial flow compressor. Okay, thermodynamic of the axial compressor stage in terms of thermodynamic relation. So the diagram shows the arrangement of blade rows for the compressor stage. So we have condition number one. At condition number one, we have the velocity diagram at the inlet of the rotor. At state number two, or condition number two, we have the velocity diagram at the outlet of the rotor. Okay. So in terms of work done by the rotor on the fluid due to the compression process in the compressor, so we have this formula that represented by equation number one, where work done delta W equal to W dot divided by M dot. M dot stand for the mass flow rate, and equal to the stagnation enthalpy difference at the outlet of the rotor and also at the inlet of the rotor, where delta W equal to H02 stagnation enthalpy at the outlet of the rotor minus H01 stagnation enthalpy at the inlet of the rotor, and also equal to, if you based on the Euler equation, delta W also equal to U multiplied by bracket Cy2 minus Cy1. Okay, Cy2 the y component or tangential component for vector C2, and Cy1 is the y component or tangential component for vector C1. Okay, so the value of Cy2 and also Cy1 we can obtain from the velocity diagram at the inlet and also outlet of the rotor. So the work done formula represented by equation number 1. If we look at HS diagram for the compression process, so we'll have the actual compression process from state number 1 to state number 3, and also the ideal compression process start from state number 1 to state number 3SS. So S stands for isentropic condition, SS stands for stage isentropic condition. So in this diagram we have numbers of points that based on the different type of pressure, static pressure, stagnation pressure, and also relative stagnation pressure. So in this diagram also we have the kinetic energy terms based on relative velocity W, and also based on the absolute velocity C. Okay, similarly as enthalpy relationship as the axial flow turbine, so the compressor also will have similar relationship in terms of enthalpy difference, where across the rotor for the compressor, the relative stagnation enthalpy is constant, where we have H01 relative equal to H02 relative, represented by equation number 2. So if you look at the HS diagram, so the point for H01 relative and also H02 relative is located on the same horizontal line, which shows that the value of H01 relative equal to H02 relative. We know that the basic equation for relative stagnation enthalpy is represented by equation number 3. H0 relative equal to static enthalpy plus half relative velocity square, W square. And if we substitute equation number 3 into equation number 2, so we'll get equation number 4, where H1 plus half W1 square equal to H2 plus half W2 square. Okay, H1 plus half W1 square equal to H2 plus half W2 square. Across the stator, the stagnation enthalpy is constant, where H02 equal to H03. Okay, the stator, where stagnation enthalpy at the inlet of the stator equal to stagnation enthalpy at the outlet of the stator, represented by equation number 5. And if you look at the axis diagram, so the point for H02 and also H03 located on the same horizontal line, that shows that the value is equal. And we know that the basic stagnation enthalpy formula is equal to H0 equal to static enthalpy plus half absolute velocity square c square, represented by equation number 6. So if we substitute equation number 6 into equation number 5, so we'll get equation number 7, h2 plus half c2 square equal to h3 plus half c3 square. So if you look at the axis diagram, so we have h2 plus half c2 square equal to h3 plus half c3 square. So these are the relationship in terms of thermodynamic relationship for the axial compressor stage. Okay, in order to test your understanding for part number 1, chapter number 5, please answer the question below. First question, what is the obvious difference in terms of work done equation for axial flow compressor compared to the axial flow turbine? Question number 2, what is the obvious difference in terms of velocity diagram for axial flow compressor compared to the axial flow turbine? Question number 3, what is the obvious difference in terms of blade row arrangement in a stage for axial flow compressor compared to the axial flow turbine? So please answer the question. So you have to answer the question by clicking the link provided in my blog. Remember that you need to know the password in order to obtain the link. The password was given throughout the video related to this topic. The clue is also given in the link. So that's all for part number 1, chapter number 5. Assalamualaikum.